Hello and welcome to the EMC Live webinar, a practical guide to EMI shielding for electronic devices. My name is Belinda Stashukevich and I'm editor of Interference Technology, the creator of EMC Live. EMC Live is an online 3-day event hosted by Interference Technology. Featuring practical information and topics, this event will include roundtables, webinars, and videos on everything EMC related, and there's no cost to attend. Join us for our other webinars this week. This webinar is presented by Wurth Elektronik. Jorge Victoria is the EMC E3 Product Manager for EMC Components and Inductive Solutions at Wurth Elektronik, headquartered in Waldenburg, Germany. An electronics engineering graduate of the University of Valencia, Spain, and he has a master's in engineering. Jorge is also a member of the IEEE EMC Society, a member of the TC7 Low Frequency EMC Technical Committee, and the SC1 Smart Grid Special Committee. This webinar is one of many. To check out our others, visit emclive2015.com. A recording of this webinar and downloadable PDFs will be available on our website shortly. This webinar will be interactive. You will be able to ask questions, and we encourage you to participate. Take a look at your GoToWebinar navigation pane, the box in the corner of your screen. If at any time you have a question, we ask you to fill out the type box and hit send. To make the screen minimize and maximize, click the arrow button. To raise your hand to ask a question or to report an issue, click the hand icon. We will present the topic for 35 minutes, followed by a 10-minute question and answer session. Now Jorge will begin the presentation.
Okay, thank you, Belinda, for your introduction, and welcome everyone to this webinar that we have called A Practical Guide to EMI Shielding of Electronic Devices. So today we will start making a short introduction about the concept of EMC shielding, and then we will go through the most common EMC problems and their shielding solutions, like joints and seams, ventilation, displays, cable entries, and PCB level shielding. Finally, we will give an extra step going to the new innovative technologies and the new innovative shielding that we need to deal with them, like wireless power charging or near field communication. So what is EMC shielding? Well, shielding is not just placing copper tape everywhere. Copper can be useful sometimes when properly used, but shielding is much more than that. We could say that EMC shielding is the art of designing and placing a shield between our device and the environment in order to increase the electromagnetic compatibility. So something a little bit more complex than just taping the copper tape. So by designing, we understand the selection of the proper materials. To choose the proper shielding materials, we have to take into account the electrical properties like conductivity, permeability, and permittivity, and take care that these properties are always frequency dependent. This is important to remind. Also the galvanic properties and the mechanical properties like flexibility and mechanical resistance are important when designing the shield. And last but not least, the shape. The shape must fit our device and sometimes also need to look cool enough. By placing, we understand the fixing method. This for shielding is quite important. We can use adhesive, we can solder the shield and screw it or just assemble it. And depending on the correct use of the fixing method, the shield will be more or less effective and it will last more in time. The other important concept in placing is where we place the shield. When we know exactly in our device where is our EMC problem, where we have our noise emitter or where we have our sensitive part, then we can just go and shield this critical part and the solution will be cheaper and more effective. Sometimes it's not so easy, we don't have this information or the shield is not enough, so we have to go further and shield at the PCB level, the device level, the system level, or even shield the complete building like happens in the military buildings or security buildings. So now we know a little bit about the concept. Now let's talk about the enemy. So we said that the EMC shielding will protect our device and the environment, and will protect it against electromagnetic radiation. So to make it simple, just this introduction, we will talk about the far field radiation. It means that we will suppose that our shield is far enough from the noise source to see the radiation at just a plane wave. A plane wave having the typical impedance of a electrical wave in the space, that is 377 ohms. What means that the impedance is the relation between the electrical field and the magnetic field. So we have here that the electrical field is 377 times bigger than the magnetic field. So when we have plane wave, we have a high impedance, mostly electrical wave. This is the case in most of the standards for immunity tests. So we are not so far from reality. So now we know our enemy, and let's check how can we fight against him with more efficiency. So the classical way, and probably the most effective way to shield a product, is to reflect the radiation. So the reflection, as we see here, is related with the mismatch of the wave impedance and the shield impedance. We saw that the wave impedance is high impedance, is 377 ohms. We call this high impedance. So we just need to use a shield made of low impedance materials. That can be aluminum or brass, any metal would be the work. And then we can get easily hundreds of dBs. So it's not so difficult to get a high amount of shielding with a conductive shield. So where's the problem then? If we have conductive shielding, we have hundreds of dBs of shielding attenuation thanks to the reflection. Why we need to make a webinar talking about this? So the problem comes when in our device we cannot just wrap it with copper and aluminum, because we need some cable entries, some connectors, displays, ventilations, or apertures just for maintenance or in the process assembly. So the problems you can see come every time, because all these discontinuities in the shield will ruin its performance. So forget about the 100 of dBs. When you have some apertures, you will probably never get it. So to see this effect and how to avoid it, we will have a short look to the antenna theory. When we have an electromagnetic radiated interference, we have an antenna that is transmitting, is emitting this radiation, and we have another antenna that is receiving this radiation. So sometimes, like in this picture, it's easy to see where is the emitter and when is the receiver, but sometimes that's not so easy. There are antennas in disguise in our device that are giving us the problem, both radiation and immunity. So let's have a look, how can we find them? So here is a typical dipole antenna. So how it works? We have a alternating field generated between two long conductors. These conductors should be long enough to resonate at the frequency of the emitter, and the excitation of the field is resonating and sent into the air. To have a good antenna, this is the relation we have between the wavelength and the frequency. And we know that if we have an antenna that is half the wavelength, we have a perfect dipole antenna. Will be a good radiator, will emit really efficiently. If the length of the antenna is smaller, then it's not so good antenna, and we can forget about it. So what happens when the radiation comes to our shield? We have the emitter, and as we said before, is far enough from our shield. So when the radiation arrives to our shield, it's just a plane wave composed by electrical and magnetic field. We'll take only into account for the for example, the electrical field that we saw is dominant. So the electric field approaches our shield. Our shield is a conductive shield, but because we saw that is much better for reflection. And when the field arrives, the electrons move through our shield because of the force of the electrical field. The problem is that when they found a discontinuity, the charges accumulate around the aperture. And when we have these charges accumulating, you remember the case, we are generating another field. As the original field is variating, this field is also variating. So instead of reflecting the radiation, the aperture in our shield is generating a new antenna that is destroying completely the effect of our shield. So to quantify this effect, we use antenna theory, and we can model these discontinuities are slot antennas. When our discontinuities are, we can see that they are the same dimensions. Oops. Yeah, the equations are equivalent. When our aperture is half the wavelength of the frequency that is troubling us, we have a perfect antenna, we have a problem. When the apertures are small enough, then they are bad antennas, and we can still have a good shielding effectiveness. So let's think now, where can we find these discontinuities we are talking about in today's devices? As you can see, just short examples from the apartment of a friend of mine. What is more difficult is to find continuities. We can find discontinuities everywhere in the displays, cables, buttons. So what we will do today is to group the discontinuities and show how to handle them one by one. So joints and seams are one of the most problematic discontinuities because are probably the bigger ones if we don't take into account the cables. So probably when we want to assemble our device, in the assembly process, we have some joints, and sometimes also our device need to be open for maintenance purposes, just to change the batteries. So we usually have these longer joints and seams around our device. When we see it, probably we can think that it fits perfectly and we have a perfect connection. But if we take care and see it with a microscope, we will see that there are only small number of points that are giving us electrical contact. So what we have, as we saw before, are discontinuities along our device that can behave like antennas. So this is a big problem, but we have a big solution. They're called gaskets. You will find in almost every electrical device. The gaskets are conductive materials that fill the space between both sides of the joints and the seam to provide conductivity all along the connection. So there are many kinds of gaskets, and all of them use the same principle. They have a core material that gives the flexibility enough to adapt to the joint or the seam, and then they have a highly conductive surface to provide this continuity path for the electrons can go through the aperture and don't generate any electrical field. So this is an example of a fabric cover foam gaskets. We have a polyurethane foam inside that give us the mechanical properties, and around a highly conductive fabric that give us the conductivity. What is important here, not only the mechanical properties and the conductivity, but the shape. There are many, I don't know, maybe infinite designs for joints and seams, as much as designers, I guess. And for each kind of seam should be selected the best shape of the gasket, especially when it's intended to open and close many times. If we want our gasket to survive many cycles, we need to use the proper one depending on how is the seam built and how is the closing and what is the pressure applied. So we will go to the next group of discontinuities, ventilation. Ventilation is always needed in some degree when we work with electronics. Currents are flowing through resistances and some electromagnetic energy is converted into heat. So we need to provide some ventilation, and how can we do it without create discontinuities in our shield? Well, I think probably we can't. What we can do is minimize the effect of these discontinuities. As we have seen, re-radiation that brings our shield is related with the length, because the electrons try to go through the aperture, but they have to divert their direction and then generate this radiation because of the slot antennas. So we can minimize it using circular shapes instead of long lines, because for the same area we can have a much smaller length, and then the electrons needs to divert their path less. This sounds good, but usually one hole is not enough. We need to use many of them. Here we have a table that I took from the book Electromagnetic Compatibility Engineering from Henriot, to give us an idea about how playing with the length of our ventilation apertures, we can have good shielding at different frequencies. For bigger frequencies, we will need small holes. For smaller frequencies, we can have bigger holes. As I said, when we use many holes, then I told before, the problem is that the electrons will divert in more places, so the shielding effectiveness will be reduced. From the same source, we have here just an overview of how it's affecting the number of holes to our shielding effectiveness. One good solution to provide enough ventilation without ruining our shield is to use a matrix of apertures. Why? Because, as I explained to you, the electrons are coming and they are diverting their path, and this is the problem we have. But if the electrons come in this direction, they divert once, but not anymore. So we count the number of holes that we need to calculate the shielding reduction. We don't have to take into account the whole number of holes, but only the maximum number of holes in one direction. So with this principle, we can ventilate our device using holes and organize them by matrix. So going to the next big group, displays. With displays, we have a similar problem. It's difficult to see through a metallic shield. So this is partially solved with the conductive coatings that are used in some EMC displays. But this works mostly for high frequencies. Usually need to be combined for lower frequencies with conductive mesh. The principle of the conductive mesh is similar to the concept we saw before. We just need the mesh as small as possible depending on the frequency, and with this structure minimize the radiation. What is critical in displays is how we connect them to our enclosure. The thing is, if it's not properly connected, this mesh around our enclosure, we will have a really big discontinuity, a really long apertures around the display, and displays behave like really, really good radiators. So what we have to do, the same what we saw before with the seams and the joints. Use gaskets or similar solutions all around the display. Usually displays have in the border the copper tape or a connection connected to the mesh that makes it easier to connect with the gasket to the enclosure to provide a direct path to the electrons. So then we go to one of the most dangerous problems when we have a shield And this is the cable entry. Sorry. So probably most of our cables will be shielded to solve also the radiation problems. Cables are also long antennas and are a really critical point. And when they arrive to our equipment, we usually have two options. We connect the shield of the cable directly to our enclosure, or we connect it to the ground plane of our PCB. In both cases, if we use a connection like the one in the picture, we will generate a big problem. When we make a connection like this, called also pigtail, you will probably heard not about it, we are introducing a parasitic inductance that with frequency will increase and will generate an impedance between the two ground planes supposed to be equipotential. We will have a current here. This will be common mode current that will flow through the shield of our cable. That is a perfect antenna. So instead of improving our device, if we do a connection like this, probably we are generating more problems than if we use just a non-shielded cable or just we didn't connect the shield to the ground. This is one of the, I think, should be one of the biggest problems, but it still happens every time. How we deal with it? Usually we arrive with a cable to our device. We have two ways, with a connector, or we pass through the enclosure and connect inside directly. For the connector, we have to assure that we are connecting 360 degrees around the connection. As we saw before, can look like we are making a perfect connection, a PV connector, for example, but if we look it carefully, probably we have only contact in the screws and maybe in the corners. So we still have some discontinuities. We have to think the shield of the cable and the shield of our device are part of the same shield and are completely connected without leaving any aperture. So in here, conductive foams or gaskets stamped with the proper dimensions will help us, as with the seams and the joints, to have a perfect connection all around. When we use a pass-through cable, for example, a grounding clip or a EMC gland will help us to connect 360 degrees shield with the ground of the PCB or to the enclosure. So these simple solutions will solve one of the biggest problems we can have. As I told you, there are many possibilities, conductive foam, stamped, conductive gaskets. Important also when you use connectors, these connectors to be shielded, because then if you have the shield arriving to your connector and then you do this pigtail inside your connector, you have the same problem. So it's important to use shielding connectors, ground clips. Always try to don't leave any discontinuity between the shield of your cable and the shield of your enclosure. Now we go to the PCB shielding. In the introduction, I said that when we know exactly where is a noise source or a sensitive part of our circuit, it's more efficient and also cheap. Go there and just shield this critical part. For this kind of shielding, is you can use conductive enclosures, small boxes called PCB shielding. Just you can customize them to fit exactly the part of your circuit that you want to shield and just place it with different technologies. The challenge here, the problem here is when you buy a PCB shield, you have to connect it to your PCB, but your PCB shield have only 5 sides. Complete shield need 6 sides. Naturally. So the 6 sides, you have to provide it with your PCB. That means you should have a really good ground plane down the PCB shield and connect it properly, again without minimizing the number of apertures that you are leaving. This is the critical point. The shield can be very good, but if it's not placed correctly or the PCB is not designed for the PCB shield, will not work at all. So till now we go through the basic shielding applications that have been used for the last years and worked for many of the technologies. But now more technologies are coming and the challenges are different. Really high frequencies where some materials are not useful anymore, and also lower frequencies with the same problem. We will have today a quick look to two of the more trendy technologies in the moment. They are wireless power charging and near field communication. Probably you have both of them in your mobile phone already. So let's go to wireless power. So wireless power technology is quite easy to explain, and it's already widespread. Most of us have a tooth everything in our bathroom is using this wireless power technology. We have a coil in the charging unit and a coil in the device that we want to charge. And due to magnetic coupling, the magnetic flux goes from the transmitter to the receiver, and a current is generating in the receiver coil that serves to charge the battery. Quite easy now. Some advances have been made in these technologies, more efficient than ever, and now you can use it to charge mobile phones, tablets, and even cars and buses. So what's the problem here? The problem is the magnetic flux is coming from the charging unit to the receiver. That's perfect. But the magnetic flux is also going through the charging unit device and through the mobile device. And it's not so nice. This can generate electromagnetic interferences. This flux is going through our PCBs, or if you have an enclosure or a PCB ground, this flux will hit your enclosure, or if there's a battery here. So that's an uncontrolled electromagnetic radiation that's bringing problems to both devices. How to solve it? The solution is to use magnetic materials for shielding. We shield our both coils in the back with these magnetic materials. These magnetic materials redirect the magnetic flux that is concentrated only between the two coils, protecting the mobile device, the charging unit, and also increasing the efficiency of the communication, because all the flux is used to charge the device. Here we have a simulation about how is the flux distributed when we have no shield and when we have magnetic shielding materials around. You can see the difference. So if you have any sensitive device in this area, then you can have problems. Let's see now the near field communication application. It's similar, but it's not. The problem is not exactly the same. In this case, we are not working with power. We are just sending data, so it's not so sensitive to electrical field. To our devices are not so in danger. It is based in resonant frequency also, but in higher frequency. We have two coils that are the emitter and the receiver, and both are resonant at a common frequency. This 13.56 megahertz. That means that the flux at this frequency is perfectly tuned, and we can have a good communication of data without using many power. That's the good thing of the near field communication. The problem comes when there's a metal plane close to our device system, close to our emitter or close to our receiver. Because the magnetic flux, when it's going through this metal plane, is generating eddy currents. And these eddy currents are generating an opposite field. And this opposite field is reducing the inductance of our antenna. That means that the resonant frequency is moving into higher frequencies. So the communication range is reduced, or the communication is impossible at all, because the emitter and the receiver are not tuned anymore, just because we approach metal material to one of them. So it doesn't make the near-field communication so robust. Here we need a shielding solution as well. And the philosophy of the solution is the similar that we used before for the wireless power communication. We use a magnetic material between the antenna and the metal plane. We put it in the back of the antenna, so it's protected. The flux is not going anymore to the metal plane, but is going directly to the receiver. With this magnetic material, we are increasing also the inductance of the antenna, so the resonance frequency is coming back to 13.56 megahertz, and the communication is perfect again, and the communication range is restituted. So let's see a little bit how this magnetic shielding works. So let's introduce the permeability. This is the characteristic that define a good magnetic shield. Permeability is the ability of the material to concentrate the magnetic flux. We talk normally about relative permeability. That is the permeability of the material related to the permeability of the air. So we can see how much is permeable our material compared to the air. So how will it attract the magnetic flux? So here we have a typical graph of the permeability of one magnetic shielding material. To understand better their performance, we divide the permeability into two parts. This is the ideal part, that is the, if we suppose that there are no losses, is the ability of the material of concentrating the magnetic flux and then reflecting it. This is the mu prime. And then we have the lossy part of the permeability, that is the mu double prime, that gives us an idea of how much of the flux that is contained in the material is absorbed and converted into heat. So with these properties, we can choose the best material for our application. For example, if we are working at 2 megahertz, then we know that our shield will be really good with reflection and we will have no absorption. That's good, for example, for wireless power, because we don't want absorption, because that will reduce our efficiency. But if we have a noise in a frequency that we want to absorb, then we will look for a high mu double prime. So playing with these materials, we will have different curves and can give you different solutions for reflecting or absorbing depending on your needs. It's a really powerful solution. So before we finish, I would like to remark that shielding is a very efficient solution for EMC problems. We can have really big attenuation. Compared with EMC filters, benefit of the shielding is that we are not reducing the speed of our digital signals. So this is much better. We don't need to redesign or retest. So we have seen the most common challenges, but we have also seen that there are solutions available for all of them. So this was just a short introduction. I hope it will encourage you to learn more and take advantage of this EMC tool. So thanks for attending, and we can go on with the questions now. Belinda.
Thank you so much, George. We'd like to have a call for final questions from the audience. Please enter any last questions you may have in the navigation pane. We have received quite a few inquiries on where to get additional information on this topic. There's a vast amount of content found on our website, emclive2015.com or interferencetechnology.com. You can also email us at info@interferencetechnology.com with specific needs, and we can direct you accordingly. George, here's a question for you. Regarding the magnetic shielding, how can I decide the thickness of the ferrite shield?
Well, it depends. I think is the answer for all the EMC questions. It depends. For example, if we are using it for wireless power, I would say that the thicker, the better, depending on how much space you have in your device, how much weight can you handle. But for example, for near field communication, it's important to choose the right one, because we saw that we are increasing the inductance. If we use too much magnetic material, we will increase so much the inductance that the resonant frequency will move too much to the lower frequencies, and we will lose our communication.
Great. Here's another question. What about the electronic devices with plastic enclosures? Are they unshielded?
So there are different solutions when using plastic. One is to paint them inside with conductive painting, but usually the other solution is to work in another level. To shield, as we saw before, we can shield in different levels. We have a plastic device, probably we have the shielding in a PCB level or in the component level. If these levels are properly shielding, then we can use a plastic enclosure without problems.
Great. Thank you so much. We have a couple other questions from the audience coming in. What is the relationship between the spaces between ventilation holes and SE?
Between SE, the spaces. It's not a big deal. We are talking about currents, about electrons. If should be too much small to be critical. I think it's not a critical parameter.
We have another question. What happens when the length is greater than lambda over 2? I'm not sure if it's over 2 or divided by 2.
Divided by 2.
Okay.
But then you have the problem, the same problem, because the longer the antenna is efficient for all the frequencies that are below. I mean, you have a bigger antenna, you are still a good transmitter. This relation gives you the perfect antenna. But if you are bigger or you are not small enough, you are still a really good antenna. So a really long cable is an efficient antenna for many, many frequencies. That's the problem. If we have a really short antenna, it's only effective for high frequencies. But if you have a long antenna, like a typical 1.5 meter cable, then it's efficient for all the frequencies that accomplish this relation.
Great, thank you. We have received so many great questions we will try to address in the future. George, thank you again for your time and expertise. Please join us next year for EMC Live 2016, which takes place next April. Webinar attendees, if you have any more questions we didn't answer here, please send us an email, info@interferencetechnology.com. A recording of this webinar will be available on our website, emclive2015.com. We will also send a link to all participants shortly. Thank you for attending.